Greetings and welcome. In this session, we will see how to solve a numerical on HVAC cooling load for case 2, that is mixing after cooling coil. In this numerical, we will find the different parameters like sensibility factors, condition of air before and after mixing by first factor, and masses of fresh air and return air along with capacity of cooling coil. So let us see statement given. Here a hall is given, air condition, condition of outdoor and room air are given, dBT and WBT outdoor and dBT and RH. Apparatus dew point of cooling coil is given. Heat content in the room sensibility, room latent heat are given in kilowatt. Infiltration air is given in meter cube per hour, and recirculated air in a percentage is given 60%. And these are the parameters already we have discussed that we have to determine. And the case is what? That is a mixing of air is done after cooling coil. So let us see block diagram. First of all, to locate the outdoor and indoor condition of the air, let us use the given data. So outdoor air, dry bulb, wet bulb temperature, this is given, we write here. Indoor condition is given, we write here. Then surface temperature, that is ADP, is given, that we write here. Now we will do the process on psychrometric chart. This treatment in the last video, that is a theoretical procedure, we have seen how to locate point OI, point A and values HO, HI, HA, VSO. These values we will find now on the psychrometric chart. So here, as per the given data, outdoor condition 38 degrees Celsius dry bulb temperature. So here is a 35, here is a 40. So here 38 comes, 38 degrees Celsius dry bulb temperature and 28 degrees Celsius WBT. Combination of these two, we get here point O, that is outdoor condition O is shown here. Then indoor condition means room condition, 24 degrees Celsius dBT, which is here. This and combination with 60% RH, 60% RH line, this line, 60%. Intersection we find. This is a point I as shown here. Then we join O to I. We draw a horizontal line through I, vertical line through O. Horizontal and vertical line intersect, we get point A. So we find the triangle OAI. Then we project point OAI, 3 points on the enthalpy scale, and we find the enthalpies of a point O, I and A from the psychrometric chart. These are shown here. We need in the numerical here to find the mass flow rate of air, outside air m dot O. So for that we need here specific volume. So to find specific volume, this is a point O. We draw this line, yellow color line, that is a parallel to the specific volume lines. One specific line, volume line is here, 0.92, and here is a 0.91. If you see this line is coming in between, so by doing the observation we can write the value, that is 0.911 meter cube per kg specific volume. We are given here apparatus dew point 10 degree, we locate that. Then we join this O to ADP line. Now as we obtain specific volume, that specific volume we use to calculate the infiltration air quantity. MI will be equal to what? Volume flow rate divided by specific volume. Volume flow rate is given in a meter cube per hour. We have to convert that in meter cube per second. So divide this value with 3600 divided by obtained specific volume. By putting the values, doing the calculation, we find infiltration air quantity in kg per second. This we use in the further calculation. Now here in the given data, all heat sources are given sensible heat and latent heat in kilowatt. If you see this triangle, this I to A, this part is a sensible heat and this OA part is a latent heat. So in the room, heat load by consideration with infiltration load sensible, we can get by adding this m dot I multiplied by this sensible heat HA minus HI to the sensible heat given. So this is what room sensible heat calculation. So by putting the values and doing the calculation, we find value in kilowatt. Same procedure we do for the RLH, room latent heat, will be equal to latent heat given in the numerical plus m dot I, we already calculated, multiplied by this enthalpy difference of this vertical line, means HO minus HI. HO minus HI we obtained in last slide. We put the value and we get the answer in kilowatt. Thus we find the heat loads, that is RSH and RLH. These loads we use to find the room sensibility factor. Room sensibility factor formula is room sensible heat plus divided by room sensible heat plus room latent heat. So last slide calculated value of RSH and RLH we put here in the formula. We find room sensibility factor value. This value we locate on the sensibility factor scale. It is 0.72. So here it is coming between 0.70 and 0.75 here. This point we give the name B. Then we locate point A as an alignment circle, which is a combination of 26 degrees Celsius dry bulb temperature and 50% RH. Then we join this line AB. This line is a reference line to draw room sensibility factor line in a further step. So here the line AB, which we had, line AB, this line, room sensibility factor line, here it is shown with yellow color. To this line we draw parallel line through point I, that is indoor condition point. This line we draw up to the saturation curve, 100% relative humidity curve. Then already we had here line O to ADP, red color line. This red color line and this yellow color line get intersect, and this point we get, that is a point 1. So this is a point 1 which comes, that is a mixing chamber. Before mixing chamber, point number 1 that comes. Now the condition for this point, by projecting on scale dry bulb temperature, we find here TD1. On projecting enthalpy scale, we find enthalpy, and by drawing saturation curve parallel to the saturation line, we find relative humidity. So that is these three values we put in the condition of this point number 1. So here point 1, that is condition of air leaving the cooling coil, means mixing, before mixing chamber. Before mixing chamber, we find the condition of the point from the psychrometric chart, TD1, Phi1 and H1. These values we write. Now the next step is to find the point number 2, that is after mixing chamber. So to locate that, we use now this line which we already drawn, that is I to saturation curve, and here we obtain the point number 1. Now we take reference length of this I to 1. We measure that, we write in mm. This is the length of I1 or 1I in mm. Now to locate point in the numerical, we are given recirculated air percentage, because here if you see, this is a 0.1, that is a air which is coming from the outside, means this is a fresh air, and this is a room air, room side. This is a indoor point, means room side point. So this room side point means recirculated air percentage is given. This percentage 60% given. Now this percentage we know in a theory, we show on the opposite side, means 1 to 2. Means from this concept we take or we use the formula, that is length 1 to 2. will be equal to what? Return air percentage given multiplied by this total length. That is already we measured. So return air percentage given 60% that we use here, and this length total. By putting this and doing calculation, we find this length of 1, 2. Means this point 2 we locate from point number 1 at this distance. Thus we get for the point 2 values, condition, dry bulb temperature here. Here this point 2 we have located with the distance what we got from the calculation from point 1. We got here dry bulb temperature, we find here enthalpy and relative humidity. So these properties we have mentioned over here. So this is what condition of air after mixing chamber, that is point 2. In calculation of bypass factor of cooling coil, we take line OADP. On this OADP line already we have got this point number 1, that is intersection of this room sensibility factor line. So this point 1, so here 1 to ADP, this difference is the inefficiency of the coil. So bypass factor formula is what? This difference means TD1 minus ADP divided by total difference means TDO minus ADP. Now point number 1, dry bulb temperature we know, ADP is given, outdoor temperature of air dry bulb is given. So putting the values in the formula we get bypass factor of the cooling coil. Now we will see dehumidified air quantity calculation. So for that we use the enthalpies. Here this is a hall. In the hall the present load that already we have calculated, that is RSH and RLH. From the last slide we take the values, summation of these two, that load comes, that is RTH. So this load is added to the air which is passing to or entering to the hall. So this is a air which is entering, point number 2, this enthalpy we know. This air when reach to the hall, then that air enthalpy increases. This is a return air coming out from the hall. This enthalpy increases from this value to this value. So this enthalpy difference, that is HI minus H2 multiplied by dehumidified air quantity. This will be equal to what? RTH. RTH we have calculated, we put here. So in this unknown is m dot d. So by doing calculation we find the dehumidified air quantity in kg per second. This is a total air quantity passing to the hall. Now this total air is split into two parts. Fresh air quantity is outside, m dot o. To calculate that we multiply the percentage of fresh air with dehumidified air quantity. Now as in the numerical we are given recirculated air percentage 60%, means outside air percentage will be 40%. So we use here 0.4. Thus we get this fresh air quantity. Now this fresh air quantity m dot o, this is the air entering to the coil which is shown here. Now to find this return air quantity we use formula, that is percentage return air multiplied by calculated value of dehumidified air. By putting the value over here we get recirculated air quantity. Now these both quantities, fresh air and return air, we find in kg per second. Then the last is to find the capacity of cooling coil. Here is a cooling coil, before the cooling coil point O and after the cooling coil point 1. So we have enthalpies of point O, that is HO, enthalpy of point 1 means H1. These two enthalpies we put here, enthalpy difference across the cooling coil multiplied by amount of air passing over the cooling coil outside air means m dot O, which is calculated in last slide. So by putting the all values we find the value of capacity of cooling coil in kilowatt. Further, divide this value with 3.517. We find the value in TR, means ton of refrigeration, capacity of cooling coil. So all the parameters what we obtain, these are summarized here. Room sensibility factor, then condition of air before and after mixing chamber in the form of dry bulb temperature, bypass factor of the cooling coil, air entering to the hall means dehumidified air, air entering to the cooling coil means fresh air, and recirculated air. These three quantities we have obtained, and finally we obtain the cooling capacity TR. So this was the procedure to solve the numerical on mixing of the air after cooling coil. Let us meet in the next video session. Thank you.